So let's start with this. We're going to find the equation of the line tangent to f of x equal to x squared plus x at the point -3 comma 6. All right, so I think this is a relatively straightforward question. Whenever you have to find the equation of a tangent line, or really just an equation of a line, we need two pieces of information. We need a point and we need a slope. This one, right? The point's already there. They might have just given us x equal to -3, and if they did just give us x equal to -3, we would have found the y coordinate by plugging it into the function and getting 9 minus 3, which is 6. So there's our point. We also need the slope. And we're going to find the slope by taking the derivative of the function. So our derivative is f prime of x equal to 2x plus 1, and then substituting in the value of x that we're taking to finding the tangent line at. So we're going to say that f prime of 3, sorry, f prime of -3 is going to be 2 times -6 plus, sorry, 2 times -3 plus 1, which is -6 plus 1, which is -5. And then the rest of it's just remembering the either the point slope form or the slope intercept form. I prefer point slope. So I'm going to say the y, bless you again, minus the y coordinate is equal to our slope times x minus the x coordinate. Oh, sorry, slope's -5. Apologies. Gosh, I'm writing the wrong thing all the time. So y minus the y coordinate of 6 is equal to the slope -5 times x minus the x coordinate, which is -3. And usually they want us to write it in the more standard y equals mx plus 3 form. So we would write this as y minus 6 equals -5x, and -5 times +3 is -15. And then we would add 6 to both sides to get y equal to -5x, and -15 plus 6 is -9. So that's all well and good. Finding the equation of a line tangent to a curve at a particular point is usually not too terrible. It is more interesting, and someone asked a question like this a class or two ago, and I think doing another example is worthwhile to answer the following similar but very different question. So let's change it up and now say we want to find, so bonus part here, want to find the equation of the line tangent to same function, f of x equal to x squared plus x. But I'm going to change the word just a little bit here. Instead of at the point -3 comma 6, is going to be passing through the point. What have I got here? 4 comma 16. And there could be no answers, although usually they don't ask the question with answers. There could be 0, 1, or 2 answers to this question, though. There could be 1 line, there could be 2 lines, there could be no lines. We don't need to draw a picture, but I kind of like drawing a picture. So let's draw a picture. Doesn't have to be perfect. My parabola opens upwards. It looks vaguely like this. And then my point 4 comma 16, I'm actually kind of curious. Would the point 4 comma 16 be above the parabola or below the parabola? Good question. So if I plugged in 4 for x here, I get 16 plus 4, which is 20. So the parabola is going to have a higher y value at the corresponding x value. So wherever 4 is, let's say 4 is like here, maybe here is 4 comma 16. So there's probably going to be 2 answers. I keep trying to use this red pen to scratch. There's probably going to be a line like this and a line like that. But we don't, again, really need to know that to do the problem. So here's our point, 4 comma 16. And since we don't know either of the points of tangency, we're going to label them. And You could label it as x comma x squared plus x, but people usually, for whatever reason, don't use the variable x here. It just isn't done. I don't know why. I really don't know why, but it's just, we don't do it that way. We call it a comma f of a, which is going to be a comma, in this case, a squared plus a. All right, here's what I want you all to do. I want all of you to find the slope of this tangent line in two different ways. So this line here that I've drawn, oh yeah, find its slope in two different ways right now. While I let you work on that for a moment. Finish that part. So those are my two slope equations. One way I can find the slope between the point a comma a squared plus a and the point 4 comma 16 is by using the slope between 2 points equation. Difference in the y's divided by difference in the x's. So that's going to be a squared plus a minus 16 over a minus 4. I do recommend subtracting in the order where the a's are first and the numbers are second, but either way is actually fine. Just more confusing the other way, I think. The derivative of x squared plus x is 2x plus 1. So the derivative at this point of tangency, which is again a comma a squared plus a, we're just substituting in a for x. And then we're going to set them equal to each other. So we're going to set a squared plus a minus 16 over a minus 4 equal to 2a plus 1. And then what you should typically do here is just multiply both sides by the denominator. So we're going to say great, a squared plus a minus 16 equals 2a plus 1 times a minus 4. If you remember the last one we did, this is very similar, right? We're again getting the slope equal to the derivative, or I should say the slope equation equal to the derivative, and then we're having this equation, which is going to end up being a quadratic equation. Let's see what we've got here. We've got a squared plus a minus 16 equal to 2a squared plus a minus 8a is minus 7a, and then a plus 1 is a. And either we're lucky or the people designing these problems are very good, because in this case as well, oh, sorry, nope, back that up. Never mind. I was about to say something that was totally wrong. Simplifying, let's bring everything to the right-hand side. So we have 0 on the left. 2a squared minus a squared is a squared. And the a's here cancel, so negative a. So we're just left with a negative 7a. And then a plus 16. I'm a little worried. I'm a little worried because I made a mistake. I forgot the minus 4. Maybe I said the minus 4, but I totally forgot to write it. So 16 minus 4 is 12. Okay, that's a little better. I was worried because I knew that I couldn't multiply the 16 and add the negative 7. But I definitely can multiply the 12 with negative 3 and negative 4 and add up to negative 7. So we get 0 equal to a minus 3 times a minus 4. This is going to be interesting. So I either get a equal to 3 or a equal to 4. That seems interesting. I feel like I need to check my math. So here's why I'm concerned. If my point of tangency is directly above the point that's supposed to be going through, what kind of line are we going to have? If my point is, say, like 4 comma 16 and 4 comma 20. Let's say I draw it again. Yeah, right. If my points are here and here, that's a vertical line. Parabolas don't have tangents that are vertical lines, right? Even though the parabola does get very, very steep as you go further left and further right, it never goes vertical. So I feel like I must have made a mistake somewhere. Let's check. So I had a squared plus a minus 16 over a minus 4 equal to 2a plus 1. And I did the a minus 4 times the 2a plus 1. I got 2a squared plus a minus 8a is minus 7a and minus 4. Oh, I threw it. I see what I did. That a somehow, I don't know why I wrote that a there. It should have been a minus 4. So there's an extra a here. That's the problem. I apologize. I'll remind you all, as I've said a few times, if you see me making a mistake, you're really welcome to call me out. I'm not trying to usually, but as you might have noticed, it does happen on occasion. So please don't hesitate. You're like, hey, James, I think you're making an error. It's really okay. I know I'm not perfect. So let's see. So bring everything to the right-hand side. 0 on the left. 2a squared minus a squared is a squared. Negative 7a minus a is negative 8a. And negative 4 plus 16 is plus 12. Cool. This will also factor. It's going to be a minus 6 times a minus 2. So we're going to get either a equal to 6 or a equal to 2. And then we have to go back and find both of the tangent lines. So one of the tangent lines for a equal to 6, our slope is going to be 2 times 6 plus 1. And the point, well, we know the point's 4 comma 16. So it's going to be, how do wow, I'm really impressed with how many mistakes I just made casually. I said 2 times 6 plus 1. And what did I write? 16. 2 times 6 is 12. 12 plus 1 is 13. I think I got ahead of myself and was seeing the 16 over here. My slope should be 13, not 16. And the point we're going through is 4 comma 16. So the equation would be y minus 16 equal to 13 times x minus 4. And we could solve for y there, but that's not really the point at this point. The other equation, when a equals 2, the slope would be 2 times 2 plus 1, which is 5. Still passing through the point 4 comma 16. So then we're going to get y minus 16 equal to 5 times x minus 4. And again, both of those you could solve for y and write it in the more standard form. So what can we take away from this besides I made mistakes? It's always good to think about what your answers mean, right? If we had gone ahead with our, our point of a being 4, we would have gotten the tangent line that was a vertical line. And then we had to be like, that doesn't make sense. Parabolas can't have vertical tangents. So it's always good to think about the context of what's going on. Other functions can have vertical tangents, but specifically not parabolas, or really not any polynomial, actually. Polynomials can't have vertical tangents because they're differentiable everywhere. All right. Question. So let's remind ourselves of the chain rule. We were talking about that last time. Let's see here. I've got some good ones. Yeah, let's look at that. Let's say we want to find, I like this one. Find f prime of x for, what have I got here? Yeah, sure. F of x equal to secant of e to the 3x plus x squared. I feel like secant is always, well, let's make it even harder. Yeah, let's make it harder. Let's make it secant to the fourth of e to the 3x plus x squared. Extra ugly. So whenever you have a trig function to a power, I would always recommend rewriting it. I would always take the step to rewrite it as f of x. I'm not taking the derivative yet, so I'm not going to write f prime equal to your trig function of its argument. So secant of e to the 3x plus x squared, all of that raised to the power of 4. And then that's always a worthwhile step, or at least make sure you're thinking of it that way if you don't want to rewrite it. Now we're ready to take the derivative, and it's going to be long. So I've got some stuff to the fourth power. The derivative is 4 times all of that stuff to the third power, multiplied by the derivative of the inside stuff. So now when I think about the derivative of the inside stuff, I'm essentially looking at this with fresh eyes. I'm like, okay, my new inside function is secant of e to the 3x plus x squared. Or in other words, secant of some stuff. Or if you want to say, we can say secant of some new stuff. And we know that the derivative of secant of x is secant of x times tangent of x. So the derivative of secant of some stuff is going to be kind of grossly secant of the stuff times tangent of the stuff. The stuff does show up twice. Stuff is e to the 3x plus x squared. Again, it's e to the 3x plus x squared. And now we have to multiply by the derivative of the inside stuff. Only once though, right? Even though it's showing up twice, we're only multiplying by the derivative of the insides once because that's how the chain rule works. And then for the inside stuff, it's actually, there is a mini chain rule in there as well. So certainly the derivative of x squared is 2x. But the derivative of e to the stuff, e to the 3x, is going to be, well, the derivative of e to the x is e to the x. So the derivative of e to the stuff is e to the stuff, but then we have to multiply it by the derivative of the stuff, which is 3. But that 3 only multiplies the e to the 3x, not the entirety of e to the 3x plus 2x. Gross. So I would definitely recommend, yeah, let's do one more. Let's say we have something like g of x equal to x cubed over cotangent of x plus x to the 5th to the third power, to the 13th power. I changed it because if the powers are the same, I'd probably just write the whole thing as being to the third power, and that feels a little less necessary to do this way. Should we simplify this? Maybe. You could certainly rewrite this as x cubed multiplied by cotangent x plus x to the 5th raised to the negative 13th power if you found that more convenient. I don't think it's better one way or the other. So without any kind of guidance, I would probably choose to leave it as is if there wasn't a good reason to change it. So I'm just going to start taking the derivative using the quotient rule. So let's see, it's going to be the bottom. Cotangent of x plus x to the 5th, all to the 13th power, times the derivative of the top, 3x squared. Okay, easy so far. Second part's going to be a little less easy. Minus, now we switch it. We leave the top part alone, so x cubed. We multiply by the derivative of the bottom part. So the bottom part is some stuff raised to the 13th power. Its derivative is going to be 13 multiplied by that stuff to the 12th power. Stuff stays. So this is, I'll point out here, one of the most common mistakes people make when they're doing this, when they're using the chain rule, is they take the derivative of the inside stuff and put up like people often right here would write negative cosecant squared x plus 5x to the 4th. We have to leave the stuff alone. Basically, the argument should be showing up again. So the insides here don't get changed. It's just cotangent of x plus x to the 5th. But then after that, we have to multiply by the derivative of that inside stuff, which is exactly negative cosecant squared of x plus 5x to the 4th. Divided by the denominator squared, so it's going to be cotangent of x plus x to the 5th raised to the 26th power. Should not simplify this unless you were asked to. But if you were asked to simplify this, the first thing you would do would be to factor out a cotangent x plus x to the fifth to the 12th power from each of the two pieces on top. That would be an easy first simplification. Yeah, let's go ahead. So normally I would say don't simplify it, but let's show that one step because I feel like that's something people could bear to see. So I'm going to factor out a cotangent of x plus x to the fifth to the 12th power, always the lesser amount. I guess I could also factor out an x to the second. Here's what we're left with. It's going to be kind of gnarly. We're going to have a 3 times a cotangent x plus x to the fifth. Minus an x times 13. None of the cotangent x plus x to the fifth because we pulled all those out over here already. But then we do have a negative cosecant squared of x plus 5x to the fourth. All divided by cotangent of x plus x to the fifth raised to the 26th power. And actually what I really want you to see from all of this is that when you use the quotient rule and your denominator already starts out with something raised to a higher power, if you simplify it, what will end up happening is the denominator power will have increased by exactly 1 every time, right? If I cancel this to the 12th here and 12 of them here, I'm left with 14, which is exactly 1 larger than 13. That is not a coincidence. That always happens when you use the quotient rule. Is the thing in the denominator, its power increases by 1 if you do the simplification of all the stuff. Kind of neat. So we're not going to, but I will tell you that if we took the derivative again, like we took the second derivative here and simplified it enough, we'd eventually get to a place where the denominator was cotangent x plus x to the fifth raised to the 15th power. Kind of neat. Yeah. Yes. So it depends on what you're asked to do. But usually with problems this gross, they usually say something like, find the derivative and do not simplify. So I would definitely typically leave it like this. I remember last class, there are a few questions about how we factored stuff out. So I thought I'd give another example of that to make sure people kind of see that again. But really, it's mostly about reading the instructions. So it's what is being asked for. Let's see here. Look at that. We're good there. Cool. Ooh, yeah. All right. So, yeah, let's continue on. So I know we've talked about the derivatives of most functions, except for, we still haven't talked about natural log of x yet. And then there's like 3 other functions that are kind of important. We'll talk about the inverse trig functions, but those are a little bit later, not quite yet. So let's look at, So let's talk about, that's where I want to be. Sorry, 1 second. I just need to, let's talk about implicit differentiation. And the big idea with implicit differentiation is that we're going to assume that y is a function of x, whether or not we can explicitly write it that way. So the example we usually start off with is, let's say that we want to find slope of the line tangent to the circle x squared plus y squared equal to 25 at the point 4, -3. So first off, the circle is not a function, right? It fails the vertical line test hard. Doesn't mean it doesn't have any tangent lines. If I draw this circle and go over to the point 4, -3, there for sure is going to be a tangent line there with some defined slope. So our job is to figure out what's the slope of that. Okay, we're going to do this 2 ways. The first way is going to be maybe the normal-ish way, or the way we think of as normal was we're just going to solve for y. and then take the derivative, which is not always going to be an option for implicit differentiation, but in this case, it is an option. So taking our equation here, y squared is equal to 25 minus x squared. And then y is going to equal what? So I want to be careful here. If you're thinking 5 minus x, I want you to check yourself, because it's definitely not 5 minus x. Let me point out something. If I plug in the 0.4 comma negative 3, it is a satisfying value for this equation, right? 4 squared plus negative 3 squared is 16 plus 9, which is 25. If you plug in, if you think of this as 5 minus x, 4 negative 3 doesn't live on that, right? That's the equation of a line. So we, unfortunately, when you have a square root of a sum or a difference, we can't just take the square root of each part. We have to just write it as the square root of the whole thing. But I'm missing something. Because if you look at the circle, the top half of the circle is when y is equal to positive square root of 25 minus x squared. And the bottom half of the circle, where y is negative, is going to be y equal to the negative square root of 25 minus x squared. And since I'm trying to find the slope of the tangent line at the point that's on the bottom half, I should use the bottom half of my circle. I would rather rewrite this as negative 25 minus x squared raised to the 1/2 power. And now we're going to find the derivative so we can find the slope. The derivative is going to be negative 1/2 times 25 minus x squared to the negative 1/2 times the derivative of the inside, which is going to be negative 2x. And not that we need to simplify it here, but I do want to simplify it just to make it look a little bit nicer. A negative 2 cancels a negative 1/2, so we get just x divided by 25 minus x squared to the positive 1/2. And now, if we plug in, what was our point? 4 comma negative 3. So if we plug in x equal to positive 4, we're going to see that y prime evaluated at x equal to positive 4 is going to be 4 divided by 25 minus 16, the square root of 25 minus 16. 25 minus 16 is 9, the square root of 9 is 3, so we get positive 4/3. And certainly, our line looks like it has a positive slope, right? It's definitely positive. I will point out that if we had looked at the point 4 comma negative 3, sorry, 4 comma positive 3, excuse me, with the same x value, the way we get the right slope there is by using the other piece of the function. So the fact, or the other piece of the circle. The fact that this isn't a function makes it difficult to deal with. And you have to kind of think about what part of the function am I dealing with, or what part of the not function am I dealing with before I can plug in the point to find the slope of the tangent line. Or we could do something completely different. Trying to keep your notes in there. So here is another way of approaching this. We're going to pretend that y is actually a function of x. We know it's not, but it is not unreasonable to say that y depends on x in some way, right? If we knew the value of x, we'd have a pretty good idea of what the value of y was, up to maybe being off by a sign. So actually, we're going to write this way. So I'm going to take my equation. So we had x squared plus y squared equal to 25. And even though you don't really need to do this for implicit differentiation, I do think it helps you see it the first time. So we're gonna rewrite this as x squared plus f of x squared equal to 25. And whenever you're using implicit differentiation, the first step is typically just to take the derivative of both sides of your equation. Don't try and solve for y, it's usually impossible. Just differentiate. If we differentiate both sides, the derivative of x squared is 2x. The derivative of some stuff squared is 2 times your stuff to the first power times, thank you, the derivative of the stuff, equals 0, right? The derivative of both sides. The derivative of 25 is 0. Or if you didn't want to use this f of x notation, you could have said 2x plus the derivative of y squared is 2 times my stuff times the derivative of my stuff equals 0. Usually we use this notation, but it's kind of nicer to see, oh yeah, the chain rule really does apply here because we're thinking of y as a function of x. And then the next step is to solve for the derivative. So we're going to solve for the derivative here. So we're going to subtract 2x. So we have the 2 times f of x times f prime of x is equal to negative 2x. And then divide by 2f of x to get that f prime of x is equal to negative 2x divided by 2f of x, which is just negative x over f of x. Or in this case, if you prefer, 2y prime equals negative 2x. Y prime equals negative 2x divided by 2y, which is just negative x over y. Same thing, just different notation. And now we're going to plug in the point of tangency. So if we plug in the point 4 comma negative 3, we can see that y prime evaluated at 4 comma negative 3 is going to be negative 4 over negative 3, which is the same number we got before. And we didn't even have to think about which piece, the top or the bottom of the circle we were using. It kind of happened automatically for us because we plugged in y equal to a negative value, which meant we had to be using the bottom piece. So implicit differentiation actually has a lot of upside to it. There's not a lot of things. And also, this is kind of a very unique case here. Most of the time, when you're being asked to use implicit, you can't even solve for y anyway. I will point out, in this case, if you want to go one step further, we could actually plug in what we found y to be. We found y to be, I'll remind you here, y was negative square root of 25 minus x squared. So if we plug that in here, you get negative x over negative square root of 25 minus x squared, and then the negatives cancel, and you get x over the square root of 25 minus x squared, which is exactly what we got up here. Same derivative. Kind of neat. Not that important though, as far as you don't have to make them reconcile because we're almost never going to be doing that. So let's see here. Let's look at some more examples. Oh, sure. Here's a classic example. Yes. Yeah, sure. This example is probably in your textbook. This one is called the folium, I don't know, the folium of Descartes. The equation is x cubed plus y cubed equal to 6xy. And oh yeah, question. Yeah, sure. The reason I imagine that people like to do this example is because it's something that we're relatively able to graph. A lot of these implicit equations are really impossible to graph, at least by hand, without using a tool. But this one's really easy. Also, I will point out, Desmos can graph things that are implicitly defined. You could totally throw this into Desmos and it would graph it just fine, or really any of these things, as long as they are reasonably well defined. If you just try typing in whatever your implicitly defined equation is, you can usually see what the graph looks like. And some of them are really kind of wild looking. I would encourage you to, it's kind of neat. But here, this one is pretty easy to graph. I know 2 of the points on it. 0, 0 is a point, and so is 3, 3. Because 3 cubed plus 3 cubed is 27 plus 27, which is equal to 6 times 9, which is 54. And I'll do my best to draw it here. It looks kind of like this. Ooh, kind of being a stretch here. Kind of what it looks like. Clearly not a function. So we can ask questions like, find the slope of the line tangent at the only point we really know, 3, 3. Okay, well, just like before, we're going to assume that y is a function of x. We're going to differentiate both sides of this, assuming that y is a function of x. And x is just the usual good old x, right? So differentiating both sides, we get 3x squared plus the derivative of some stuff cubed is 3 times our stuff squared times the derivative of our stuff equal to the derivative of 6x times y. I'm going to think of 6x as one piece and y as the other piece, although the 6 could just live out in front either way. The derivative of 6x is 6 times leave y alone because we're using the product rule, plus 6x, we leave it alone. And what's the derivative of y? It's the derivative of y. That one always used to kind of make me like, what? Oh, yeah. Some people will be like, it's 1 times y prime. The way you should think of this is whenever you're differentiating something with y in it, at the end of the process, you're always going to have to multiply by y prime. But the derivative of y is just y prime, the derivative of y. How do I want to do this here? Yeah, I'll do it the fun way. So then we're going to solve for y prime by bringing all the terms of y prime to one side and all the terms without y prime to the other side. It's kind of like when you find an inverse function. You bring all the y's to one side, you factor it out, you solve. Here, now we're solving for y prime. So bring all the y primes to one side. So I have 3y squared times y prime minus 6x times y prime equal to 6y minus 3x squared. Factor out the y prime. So y prime times 3y squared minus 6x equal to 6y minus 3x squared. Divide both sides by that. And usually that's about as far as you can go. In this particular example, there is one more thing we could do. We could factor out a 3 from the top and the bottom and cancel it and say that it's equal, that y prime is equal to 2y minus x squared over y squared minus 2x. So if we want to plug in our point of tangency, which is 3, 3, y prime at y, James, come on. Y prime evaluated at 3, 3 is going to be 2 times 3 minus 3 squared over 3 squared minus 2 times 3. And negative 3 divided by 3 is negative 1. And that doesn't look too surprising because if you drew the tangent line here, yeah, that seems like that tangent line could have a slope of negative 1. Seems very plausible. Here's an interesting additional question. Where's the highest point on the loop? Well, it's not there because and maybe I drew it kind of poorly, as is expected, but it probably keeps going up a little bit like that. There's probably a higher point like right there. So where is the highest point on the loop? Or in other words, where is the derivative equal to 0? Okay, so we're going to set 2y minus x squared over y squared minus 2x equal to 0. And well, we certainly know the point we're looking for isn't the origin, although it's probably true that in one of these directions, like in this direction this way, the slope of the tangent line that way is 0. Slope of the tangent line this way is probably undefined. But we're looking up here, so we're not worried about that. If you're trying to set something equal to 0 that's a fraction, we specifically want the numerator to equal 0. So really that's going to be 2y minus x squared equals 0, or 2y equals x squared, or y equals x squared divided by 2. Which doesn't seem like it's super helpful. We have to remember the point we're looking for is on an equation that's already been defined. So we're saying, oh, wait, we know that we also need x cubed plus y cubed to equal 6xy. So now what we have to do, which is kind of weird, is plug in y equal to x squared over 2 for each of the y's. So we can solve for x. Yeah, it's kind of gross. I feel like I say that word a lot in this class, but there's a lot of gross things. The math is just not always pretty. So here, we're going to have x cubed plus x squared over 2 cubed equal to 6x times x squared over 2. Simplifying a bit, We have x cubed plus x to the sixth over 8 equal to 6x times x squared is 6x cubed divided by 2 is 3x cubed. Bringing everything to the left-hand side. Left-hand side? No, yeah, sure. We have x to the sixth over 8. X cubed minus 3x cubed is minus 2x cubed equal to 0. We can factor out what? What's the biggest power of x we can factor out? The third power. So we're going to rewrite this as x to the third times x cubed over 8 minus 2 equal to 0. So we either get x cubed equal to 0, which we know isn't the solution we're looking for, because that's definitely not the point on the loop we were talking about. Not that. Or x cubed over 8 minus 2 equal to 0. So that means we're going to get x cubed over 8 equal to 2, x cubed equal to 16. X is going to be the cube root of 16. Gross. And they asked for the point, not just the x coordinate. Then we're going to find the y coordinate by plugging it back in here and saying that y is going to equal the cube root of 16 squared over 2. Or if you prefer, you can say this is 16 to the 1/3, and this is 16 to the 2/3 over 2. So the terrible point that we found is 16 to the 1/3, comma, 1/2 16 to the 2/3. So here's another example. Yeah, there we go. Sorry, I'm just trying to find the example I'm looking for. Here we go. So let's look at a more typical example of a implicit differentiation question. And I feel like there's kind of two varieties here. Let's look at this first one. We want to find y prime for the equation x squared y cubed plus cosine of x equal to x to the fifth minus y to the second. So our job here is simply to do the following things. Differentiate both sides, isolate y prime, solve for y prime. So first, differentiate. Usually there's some product rule involved. Here for x squared y cubed, we're going to get 2x times y cubed plus x squared times the derivative of y cubed is going to be 3y squared times y prime. The derivative cosine of x is negative sine of x equal to the derivative of x to the fifth is 5x to the fourth minus the derivative of y squared is 2y to the first times y prime. And then I'm just trying to kind of look and see like which things I'm looking at. Okay, that and that are my y primes. So bring all the y primes to the same side, all the other stuff to the other side. I think this next step you could actually, or these next two steps you could probably do in one step. So we're going to bring everything, all the y primes to the left and say we have 3x squared y prime plus 2y times y prime equal to all the other stuff on the right. 5x to the fourth minus 2xy cubed plus sine of x. In my opinion, we also could have factored out the y prime on the left-hand side in this step. So on the left-hand side, now we have y prime times 3x squared y squared plus 2y equal to the same stuff. And then finally, we divide both sides by whatever's multiplying y prime to get our kind of terrible derivative is 5x to the fourth minus 2xy cubed plus sine of x over 3x squared y squared plus 2y. And that's our final answer. Our derivative in these implicit problems will almost all the time be in terms of both x and y. There's no avoiding. So here's a different take on a similar-ish question. Let's say instead we were asked the following. We want to, where'd you go here? Yeah. Find the equation, let's say slope. Find the slope of the line tangent to, what's my equation here? X plus y to the fifth equal to x times y plus x cubed plus 2y squared at the point -1, 1. So how do we find the slope of a tangent line? We take the derivative. So we're taking the derivative. Well, we're going to start by taking the derivative in exactly the same way we have the first couple times. So we're going to differentiate both sides. So let's see, I've got some stuff to the fifth power. The derivative is going to be 5 times my stuff to the fourth power times the derivative of the inside stuff, which is going to be 1 plus y prime, equal to, okay, for x times y, we have to use the product rule. Derivative is going to be 1 times y plus x times the derivative of y plus the derivative of x cubed is 3x squared plus the derivative of 2 times y squared is 4 times y to the first times the derivative of y. Now you have options. You could do the same thing we've done the previous 2 times and solve for y prime. We'll do that first to show you why you shouldn't do it. So let's solve for y prime. Okay, this one's extra terrible because I have a 1 plus y prime in parentheses here. So I have to distribute the 5x plus y to the fourth to each of those two terms there. So I have 5 times x plus y to the fourth times 1 plus 5 times x plus y to the fourth times y prime equal to y plus xy prime plus 3x squared plus 4y prime. And then all of the terms of the y prime have to end up on the same side. So I am going to do 2 things at once here. I'm going to bring all my y primes to the right, everything else to the left. I'm also going to factor out the y prime from the y prime terms on the right. So on the right-hand side, I would have had x times y prime plus 4y times y prime minus 5 times x plus y to the fourth times y prime. But instead I'm factoring out the y prime from all of those like that. On the left-hand side, I have my 5 times x plus y to the fourth minus y minus 3x squared. And then we're going to divide everything by this to get that y prime is equal to 5 times x plus y to the fourth minus y minus 3x squared divided by all that. X plus 4y minus 5 times x plus y to the fourth. Finally, we can plug in the point of tangency to find the slope of the tangent line. So y prime evaluated at -1, 1 is going to be, let's see, 5 times -1 plus 1 to the fourth minus 1 minus 3 times -1 squared divided by -1 plus 4 times 1 minus 5 times -1 plus 1 to the fourth. That's going to be, let's see, 0 minus 1 minus 3 divided by -1 plus 4 minus 0. That's going to be -4 divided by +3. It's -4. Why am I writing it again? Okay, all that to show you that we didn't need to do all that. Here's why. We're trying to find the slope of the tangent line at a particular point. There's no rule saying that we have to wait until the very end of the process to plug in the point. Once you've taken the derivative, we can plug in the point right away and then try and solve for y prime. So I'll point out that if we take this equation after we've differentiated both sides, and we just say, hey, cool, let's go ahead and plug in x equal to -1 and y equal to +1. Well, some nice things happen. -1 plus 1 is 0. 0 times anything is 0. So the whole left-hand side here is a big old 0 equal to 1 times y, which is 1 times 1, plus x times y prime, so that's going to be plus -1 times y prime, plus 3 times x squared, that's going to be 3 times -1 squared, plus 4 times 1 times y prime. So let's see, I've got a 1 plus 3. So I've got 0 equal to 1 plus 3, which is 4. And -y prime plus 4y prime is plus 3y prime. And then subtracting 4, I get -4 equal to 3y prime. I get y prime equal to -4/3. The same exact answer. Which one seemed easier? I have to say the second one, right? Without a doubt. So if you were asked to find the slope of a line tangent to some implicitly defined function, the usual best way to do it is to differentiate both sides first. You have to take the derivative first of both sides, but then after that, plug in the point of tangency immediately, and then solve for y prime. All right, let's see. We've got 25 minutes left. Yeah, question.
Yeah, I think I just missed something earlier. So why do you, when you're taking the derivative initially, why do you multiply by 1?
Right, exactly. So like for just as a reminder here, so when we're taking the derivative of say like, so we're really thinking of this equation here. Recall, we're pretending, we're imagining that y is some function of x. So I could rewrite this using this notation, although we don't have to, as x plus f of x to the 5th equal to x times f of x plus x cubed plus 2 times f of x squared. And then if I take the derivative of some stuff to the 5th power, I'm going to get 5 times my stuff to the 4th power, but then what do I have to multiply by? And the derivative of x is 1, and the derivative of f of x is f prime of x. Similarly, on the right-hand side, for x times f of x, I'm going to have to use the product rule. Derivative of x is 1, leave f of x alone, leave x alone, and the derivative of f of x is f prime of x. The derivative of x cubed is 3x squared, and the derivative of 2 times some stuff squared is going to be 4 times our stuff to the 1st power, and then we have to multiply by. So that's why we're always multiplying by a y prime, because really we're just saying, we're just pretending like y is a function of x. And so when you differentiate it, we're always using the chain rule, and at the end of the process, multiplying by the derivative of y. I would say, even though we call this implicit differentiation, this is really just another application of the chain. It's the chain rule all the way, which is kind of the story of maybe the rest of this class. Is it's the chain rule all the way, all the time. Chain rule, chain rule, chain rule, all the time. But yeah, that's what's going on there. Where was I going? Oh yes, that's where I was going next. Okay, so let's do that. So one of the reasons we really like to talk about implicit differentiation is because it helps us differentiate some new functions, like any function that's an inverse of another function. For example, we want to find the derivative of the natural log of x, which I might have written in the cruelest way possible because it makes it hard to see what we're going to do. So to do this, we're going to start with by saying we're going to let y equal the natural log of x. And this is a pretty standard process for differentiating a function that's an inverse of a well-known function. So we're going to rewrite this. We're going to rewrite it solving for x. So e to the y equals e to the natural log of x, giving us e to the y equal to x. Okay. Remembering that we're not even just pretending here. Y is actually a function of x, right? Y is equal to the natural log of x. So recognizing that y is a function of x, differentiating both sides, What's the derivative of e to the stuff? E to the stuff times the derivative of the stuff. What's the derivative of x? 1. Let's solve for y prime because we're trying to find the derivative here. So solve for y prime. We're going to get y prime equal to 1 over e to the y. Now, it's a little disappointing because we'd really like our answer to be in terms of the variable we started with. Our original function was y equal to the natural log of x. We prefer to write our answer as a function of x. And we can because, hey, look, we know that e to the y is equal to x. So we're just going to replace e to the y with x. So that gives us that y prime is equal to 1 over x. That's the derivative of the natural log function. So it is true that the derivative of the natural log of x is equal to 1 over x. And whenever you have a new derivative that you've learned, you immediately want to kind of think about, okay, there's my new formula. What's the chain rule version of it? Well, the chain rule version is just replace x with some stuff. So I would just say, great, the derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff is going to be 1 over that stuff. And then what do we have to multiply by? Like the answer is always the same, right? It's always the derivative of the stuff every time, right? We're using the chain rule. It's always going to be the derivative of your argument. People often write this as the derivative of the stuff on top of the stuff. Also fine. It's not the way I usually choose to write it. Okay. So let's do some derivatives. Lots of derivatives all the time. So if I want to find, say, the derivative of the natural log of secant of x, well, it's going to be 1 over my stuff times the derivative of the stuff, and the derivative of secant of x is secant of x times tangent of x. Normally, I would say don't simplify, but here the simplification is really, really straightforward. We can cancel the secant and just be left with tangent of x. I do recommend trying to keep this in your memory for next quarter, because eventually next quarter you'll talk about finding the antiderivative of things, including tangent. And it's nice to know that the antiderivative of tangent is the natural log of secant of x, because the derivative of the natural log of secant of x is equal to the tangent. That's what the antiderivative is, right? The antiderivative of something is just the thing that if you would take its derivative, the thing you would like. They literally just undo each other. The derivative of this is that. The antiderivative of that is this. Yes, I know that's not this quarter, but it seemed like a good place to say it anyway. So why don't you all try finding the derivative of the natural log of sine of x? Yeah. And I would encourage you all to simplify this one as well. So we get 1 over sine times the derivative of sine, which is cosine, and cosine over sine is cotangent of x. Cool. What if, oh yeah, I saw this terrible problem the other day. What if someone said my function y was equal to the natural log of something terrible, like x to the 5th times tangent of x over e to the 3x times the square root of x cubed plus 1. We want to find the derivative. So here's what I would say. The inside stuff is really gross, right? We definitely don't want to just throw this rule out and say it's 1 over all that times the derivative of all of that, because the derivative of all of that is product rule, quotient rule, chain rule, couple, like it's a lot of stuff. There's a point. The point is that we can use the rules of logarithms to simplify this expression into much, much easier things to differentiate. So there's 3 log rules we're going to use. I might need more room here, fine. The natural log, or any log base, but I'm just going to say natural log because whatever. The natural log of a times b is equal to the natural log of a plus the natural log of b. The natural log of a divided by b is the natural log of a minus the natural log of b. And then the natural log of a to some power p is that power times the natural log of a. And again, it doesn't have to be the natural log, it could be any base, but natural log is often the most common base we see. So now we're going to break this up. I think we can break this up in 2 steps, but I'm going to do it in 3. So we're going to get that y is equal to the natural log of the top, x to the 5th times tangent of x, minus the natural log of the bottom, e to the 3x, times, I'm going to write x cubed plus 1 square root as x cubed plus 1 to the 1/2. Now we're going to break up each of these. This is going to be equal to the natural log of x to the 5th plus the natural log of tangent of x minus the natural log of e to the 3x plus the natural log of x cubed plus 1 to the 1/2, but that should be in parentheses or brackets. Here's what I would like you to observe. When you break up a logarithm like this into its constituent pieces that are simpler, every factor in the numerator ends up with a positive natural log. Every factor in the denominator ends up with a negative logarithm, if you distribute them the same way. So the last step of simplifying, we're going to bring down all the powers. 5 times the natural log of x plus the natural log of, there's no power here, plus the natural log of tangent of x minus 3x times the natural log of e is just 3x, right? Because the natural log of e is just 1 minus 1/2 times the natural log of x cubed plus 1, right? Because the minus sign distributed to each of those 2 terms. I will say again, the factors in the numerator, x to the 5th and tangent, have positive logarithms. The factors in the denominator, e to the 3x and square root of x cubed plus 1, have negative coefficients of the logarithms. That is always going to be true. Now we're finally ready to take the derivative, right? All this has just been a simplifying process so far. The derivative is going to be 5 times the derivative of the natural log of x is 1 over x, plus the derivative of the natural log of some stuff is 1 over the stuff, times the derivative of the stuff, and the derivative of tangent of x is secant squared of x, minus the derivative of 3x is just 3. Or if you wanted to make it more complicated, you could have said it's 1 over e to the 3x times the derivative of e to the 3x, but that's a whole pain in the butt. Finally, minus 1/2 times the derivative of the natural log of x cubed plus 1 is 1 over x cubed plus 1 times the derivative of x cubed plus 1, which is 3x squared. And I will say yes again, lots of people prefer to write these things in the numerator. I don't, but that's just my preference. I like to write them afterwards to remind myself that this is how the chain rule is working, right? I'm doing the derivative of the outside function, I'm leaving the insides alone, and then after that, I'm multiplying by the derivative of the inside. And that's also fine to write. There was something else. Oh yeah. So if there are things that are complicated like that, that's a process. Now, yeah. There is something else related, which is kind of terrible. So sometimes, and I definitely saw someone doing this question the other day. What if I gave you the function, something like this, find f prime of x for f of x equal to, let's not make this too awful, 2x plus 1 to the 4th times 3x plus 5 over 7x plus 1 times 6x minus 2 to the 3rd. Really don't want to do that. It's really terrible. I mean, okay, it's like not the worst thing ever, but it's not the best. So when you have something awful like this, you can use this process of logarithmic differentiation where you take the log of both sides. So I say, great, well, that looks too ugly to deal with, but it fortunately is things either multiplied or divided together, which is easy to break up if it's inside a logarithm, but it's not inside a logarithm. So I'm going to take the natural log of both sides. I'm saying, okay, the natural log of f of x is equal to the natural log of all that garbage. Just verbally abusing functions over here. You're not a garbage function. You're perfectly fine. Okay, so then we're going to break this up. And this time I'm not going to show all the work because we know what's supposed to happen. The top things end up being positive, the bottom things end up being negative, and the powers come down. So we're going to write this as the natural log of f of x equal to 4 times the natural log of 2x plus 1 plus the natural log of 3x plus 5 minus the natural log of 7x plus 1 minus 3 times the natural log of 6x minus 2. Differentiate both sides. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Same deal on the right-hand side. You get 4 times the derivative of the natural log of 2x plus 1 is 1 over 2x plus 1 times 2. The derivative of the natural log of 3x plus 5 is 1 over 3x plus 5 times 3. The derivative of the natural log of 7x plus 1 is 1 over 7x plus 1 times 7. Minus 3 times the derivative of the natural log of 6x minus 2 is 1 over 6x minus 2 times 6. But then there is one more step we have to take. We have to isolate f prime by multiplying both sides by f of x. So then we say that f prime of x is equal to, I'm going to simplify this a little bit. F of x times 4 times 2 is 8 over 2x plus 1 plus 3 over 3x plus 5 minus 7 over 7x plus 1 minus 18 over 6x minus 2. And then you actually have to plug back in what f of x is equal to. So then all of this goes in for f of x right there. And I'd really rather not write it again because it's kind of a lot of writing. But hopefully I think we all can make that jump. Like, oh yeah, so f prime of x would be equal to that gross thing plugged in times all of that. Okay, fine, I'll write it out. And I said I didn't want to, but feels wrong not to. So that's how you deal with something gross like that that has lots of things multiplied or divided together. Is you can take the natural log of both sides and apply the process of logarithmic differentiation. This is not the only time we will use this process. This is probably the least obvious time you would use this process, actually. Yeah.
Why are you multiplying it by f of x?
Because so when I took the derivative of the natural log of some stuff, I got 1 over the stuff times the derivative of the stuff. But then I'm trying to find the derivative. So I want the f prime of x all by itself. So I'm multiplying both sides by f of x to get rid of the 1 over f of x on the left-hand side. And that almost always happens when you have a natural log of y equal to the natural log of some other stuff. Is at the end of the process, you're going to multiply on both sides by your original function. All right, what other things do we want to say here? Sure. So, logarithms. Not every logarithm has the nicest base ever. In fact, most of them don't. So, why do I keep doing this? All right. So, what if, say, something like f of x equal to log base 3 of x? I want to take the derivative of that. It's probably going to be similar to 1 over x, but not exactly the same. There's 2 ways you can handle this. One way is to remember the change of base formula. So the change of base formula says that log base 3 of x, you can rewrite it using any base you want. You know what base I'm going to use? E. So it's the natural log of x over the natural log of 3. Quick aside, this is actually super convenient if you're ever trying to find something like log base 4 of 8. Log base 4 of 8 isn't 2. But we can change the bases so that it's convenient. So we can say, hey, log base 4 of 8 is really log base. A more convenient base would be 2 divided by log base 2 of 4. Now, show me on your fingers. What's log base 2 of 8? This many, 3. Because right, 2 to the third power is equal to 8. That's what the logarithm is asking you for. It's asking you for the power to get from your base to your argument. What's log base 2 of 4? 2. Right. And I want to be super careful here. Not because 2 times 2 is equal to 4, because 2 to the second power is equal to 4, which is always super confusing with 2 and 4. It's just unfortunate that they happen to work that way. So the idea here is, oh, look, we can rewrite log base 3 of x as, I'm going to write it as 1 over natural log of 3 times natural log of x. And even though 1 over natural log of 3 is not a particularly nice number, it is a constant. Right? There's no x's there. That thing is a constant. And what do constant multiples do when you take a derivative? They hang out. So the derivative here is going to be 1 over natural log of 3 times the derivative of the natural log of x, which is 1 over x. The general formula here is that the derivative of log base b of x is 1 over x times the natural log of b. And since we're almost there anyway, might as well say the other thing. Yeah. A similar thing is true for exponential equations that have different bases. What do I mean by this? We have time. So what about f of x equal to 4 to the x? I really like to find the derivative of that. Well, just like log base 3 of x is really similar to the natural log of x. In fact, if you graph both of them, they have very similar shapes. 4 to the x is really, really similar to e to the x. They have very similar exponential shapes. Their derivatives should act similarly. We know the derivative of e to the x is e to the x. The derivative of 4 to the x, again, there's really, I know I only did the previous one one way. There's 2 different ways you could do this. We'll do this. Yeah, we're almost out of time, so we'll do it the easy way. Yeah, easy is debatable. So I'm going to rewrite 4 to the x as e to the natural log of 4 to the x. It's a pretty common trick when dealing with exponents here. And then e to the natural log of 4 to the x, I can rewrite as e to the x times natural log of 4. Right? I can use the power rule there for logarithms. Say, oh yeah, the natural log of 4 to a power, that power can come down in front of the natural log. All right, so now the derivative of e to the x is e to the x. The derivative of e to the stuff is, well, the derivative of e to the stuff is going to be e to the same stuff multiplied by the derivative of that stuff. And the derivative of x times natural log of 4 is natural log of 4. It's like taking the derivative of x times 7, right? The derivative of x times 7 is just 7. The derivative of x times 3 is just 3. The derivative of x times pi is just pi. The derivative of x times any constant, even if it's a funky constant like natural log of 4, is just that constant. Okay, one more thing. E to the x times natural log of 4 is just e to the natural log of 4 to the x, which is just 4 to the x. So really this is equal to 4 to the x times the natural log of 4. Or, stated more generally, and I'm going to write actually up above here, the derivative of b to the x, some other base, is equal to b to the x times the natural log of b. So the way I think about this is if your base is something other than e, if you're differentiating a logarithm with a different base, you end up dividing by the natural log of that base. If you're taking the derivative of an exponential thing with a different base, you end up multiplying by the natural log of that base. And technically, this formula is true whether or not your base is e. Because if your base was e, the derivative, check this out, of e to the x would be e to the x times the natural log of e, which is 1. And the derivative of log base e of x, which is natural log of x, would be 1 over x times the natural log of e, which is 1 over x times 1. So this formula works actually for any base that meets the usual criteria where your base is greater than 0 and your base is not equal to 1. Those are the usual requirements we have to have for these bases. All right, we'll talk more about this on Tuesday. No class, not that we have class, but no class on Monday, right? It's a 3-day weekend. Don't come to school on Monday. We won't be here. You shouldn't be here either.